Welcome back to this course on multi-core architectures. In this lesson I will discuss some limitations of symmetric multiprocessors, SMPs. I will also explain that although implementing cache coherence might seem simple, in reality it is really hard. I conclude this lesson with some limitations of SMPs, symmetric multiprocessors. First, a bus-based interconnect does not scale well, since the bandwidth available per core decreases when more cores are added. Furthermore, as more cores or more nodes are added, the bus needs to be made longer, and the bus latency increases with its length. So what can be done to resolve these problems? One solution that has been implemented is to employ multiple buses as sketched here. But this increases the complexity of the cache controllers. Other solutions include using a crossbar to connect all the cores or even using a small point-to-point network. Notwithstanding these techniques, SMPs with 4 to 8 cores are feasible and have been developed, but it is unlikely that SMP organizations with many more cores can be constructed. Another limitation of SMPs is that for every bus transaction, a cache lookup must be performed to see if the block is present in the cache. And these cache lookups could interfere with the normal CPU cache accesses, as illustrated here in this figure. Again, several solutions are possible and have been implemented. One solution is to duplicate the tags and to snoop in the duplicate tag array. Another solution is to employ multiple private cache levels as illustrated here. Then the CPU will mainly access the level 1 cache, and only in rare cases on L1 cache misses, which should not happen too frequently, it will have to access the L2 cache. Snoop accesses will then take place in the L2 caches. For this scheme to work well, it is needed that the content of the level 1 cache is included in the contents of the L2 cache. In other words, that the content of the L1 cache is a subset of the content of the L2 cache. This is called the inclusion property. Enforcing inclusion, however, is not as easy as you might think. A full discussion of this issue is beyond the scope of this specialization, and I refer you to my other specialization on systems in case you want to know the details. The final limitation or challenge of SMPs I would like to discuss is how do we increase the memory bandwidth? Again, the answer is caching. We place a shared cache consisting of multiple banks before the memory as shown in this figure. In addition, we employ a high-speed interconnect network between the last level private caches, the LL private caches, and the multi-banked shared cache. In fact, such an organization is almost similar to distributed memory systems I will discuss in the next lesson. Finally, a warning for the devil. After a bit of exercise, cache coherence protocols might look simple. They are not. They are extremely hard to implement correctly. The problem is that while we think they are atomic, transactions such as write misses and invalidates really are not. To illustrate some of the difficulties, suppose two processes P1 and P2 about simultaneously want to write the same cache block B present in both their caches. In this example, P1 wants to write the value 8 to the first word in the cache block, and P2 wants to write the value 9 to the second word in the cache block. The following might happen. Both processes do a lookup in their private caches, and both discover that they have a copy of the cache block in state shared. So both will issue an invalidate on the bus. Now it depends on who gets access to the bus first. Without loss of generality, I suppose it is P1. The invalidation of B will be placed on the bus and thereby broadcasted to all other caches. The copy of B in the cache of P2 will be invalidated. The invalidation might or actually should be acknowledged, and then P1 completes the write of B0 and changes the state of B to modified. P2 still needs to complete its write. It also places the invalidation on the bus, which will be received by the cache controller of P1. The cache controller of P1 now will be totally confused, to say the least. It receives an invalidation for a block in state modified, which, as I explained before, according to the MSI protocol, cannot happen. Let's think of a quick bug fix. Let's invalidate the copy in the cache of P1. So it shall happen. The copy of B in the cache of P1 is invalidated. The invalidation is acknowledged and P2 completes the write of 9 to the second word of B and changes the state of B in its cache to modified. Looks good, doesn't it? So what's wrong here? Well, we lost the write of 8 to the first word of B. It's gone forever. P1 performed a write, but it will never appear in the output of the program. Clearly, this must be wrong. In fact, P2 should not have issued an invalidate. It should have issued a write miss, because by the time it got access to the bus, its copy of B had been invalidated. This was just to give you an example of why it is really hard to design a 100% correctly functioning cache coherence protocol. Again, discussing all the issue is beyond the scope of this specialization. More about that in my specialization on multi-core systems. This concludes this lesson. Thanks for watching this video. In the next lesson, I will discuss how to design bigger, more scalable systems, which require a different kind of coherence protocol. Hope to see you back.